All right, in this video I'm going to be talking about the product and quotient rules. This is Unit 2, Lesson 2 in Cal BC. So, kind of an opening question for thought is, can you take the derivative of a product by taking the derivative of each factor? Like, is the derivative of this function 2x minus 1 multiplied by x plus 3, can you take it by just taking the derivative of each factor and multiplying them together? Yeah, and it's not going to work because I know that that's a second-degree polynomial, and I know that the derivative of a second-degree polynomial is a first-degree polynomial. So what I'm going to do, just to demonstrate this for you, is I'm going to actually distribute the 2x minus 1 times x plus 3. So I'm going to say f of x is equal to 2x squared, okay, plus 6x minus 1x is plus 5x. And minus 3. And if I were to take the derivative of that, using the power rule we learned last time, I would have 4x plus 5. Okay, so we can see that that is definitely not the same as 2 times 1. Right? So we need a way to deal with products, as far as taking the derivative. Maybe we could get ourselves a product rule. All right, so the product rule is that if we're taking the derivative of the product of two functions, we can do that by taking the derivative of one of them and leaving the other one the same. And then adding, basically taking the derivative of the other one and leaving the one the same. And it doesn't matter which one you put first or second, just as long as you take the derivative of one of them, leave the other one the same. Then you take the derivative of the other one and leave the one the same, right? Because, 2 times 3 is the same as 3 times 2, and 4 plus 5 is the same as 5 plus 4. So the order is not important, just as long as we're not multiplying f prime by g prime, right? So this is very important. This is something that you're going to need to commit to memory basically now. And of course, as we know, the best way to really remember something is to write it down or say it a bunch of times. This is not the type of thing that we're going to really say a bunch, but you're going to do the product rule so many times, it's just going to become second nature. Okay, so an example of this is, if we have f of x given by x to the third multiplied by cosine of x, then we could take the derivative using the product rule. So I'm going to say f prime of x is equal to, I'll take the derivative of x to the third first. It's going to be 3x squared, leaving cosine x the same. And I'm going to add, leaving x to the third the same, the derivative of cosine x. It's negative sine x. Now, if you wanted to, you could rewrite this as 3x squared cosine x minus x to the third sine x. You could factor out a couple of powers of x if you wanted to, but you'd be no more correct than what I've got written right here. So I'm just going to stop right there. Right, you might be sitting there saying, wait, but last time you told me it was okay to, take the derivative, with the constant multiple, but it's taking the constant multiple times the derivative. Like, we've been taking the derivative of 10x squared, and it's been 20x, or, 3 sine x, and it's 3 cosine x. So we need to be able to look at the derivative of 3 sine x and reconcile it with our product rule. So I think that's something that we could do right now. Now, if you're sitting here in class right now, I'm going to ask you to do this while I freeze the screen. Try to use the product rule on 3 sine x and see what happens. If you're watching at home, well, you should pause the video right now because the answer is just going to pop up real suddenly in about 5 seconds. Okay, there you go. So notice how, we took the derivative of 3, and the derivative of 3 is 0, leaving sine of x the same. And then we left the 3 the same and took the derivative of sine x. Okay, so it did end up being 3 cosine of x like we expected. So I always make sure to do an example like this, right, when we're new to the product rule, just to make sure that you don't do that yourself, right? See that it works the once, but remember that with a constant multiple, you don't need to try to apply the product rule. It'd just be a huge waste of time. Next, let's do an example where we write the equation of a tangent line. Okay, so it says write an equation for the line tangent to the graph of y equals 2x sine x at the point where x equals pi over 3. We can do that. Okay. We know that in order to write a tangent line, I'm going to need a couple of ingredients. I'm going to need a point, and I'm going to need a slope. And then I'm going to write the equation in point-slope form. Now, the point is going to be pi over 3, and I'm going to plug in pi over 3 into the equation for y. So I've got 2 times pi over 3 is 2 pi over 3, multiplied by the sine of pi over 3. Maybe you're over there saying, oh, no, I don't remember what the sine of pi over 3 is. I'm going to think about that for a minute. While you're thinking about it, I'm just going to draw a unit circle and point out pi over 3 is right there. Sine being the y-coordinate, that's pretty far up. It's not all the way up. Well, pretty far up is root 3 over 2. All the way up would be 1. So this is times root 3 over 2. All right. So, you know, I could say this is basically the same number. I could cancel off the 2's, right? And I could say that this is pi times the square root of 3 divided by 3. And I think I am going to do that. Now for the slope, I'm going to need to take the derivative. So I'll take this over here, and I'll say that dy dx is, okay, I'm going to need to use the product rule. So I'll start with 2x. That one looks a little easier. So the derivative of 2x is 2. Leave sine x the same. Then I'm going to add, leaving 2x the same, take the derivative of sine. Well, that's cosine x. Right? And now to get the slope, I'm going to plug x equals pi over 3 into my formula for dy dx. So this is 2 times the sine of pi over 3. And then 2x is going to be 2 pi over 3 multiplied by cosine x. Well, I look over here, and if you think about it, you know, this is the narrow triangle, narrow and tall. And cosine in that case is going to be a half. Not very far over. Not very far over is half. So I could probably rewrite this. I could say that this is square root of 3 plus pi over 3. You know, it's a pretty ugly number, but it's nothing to be scared of. So if I've got a point and a slope, I can write an equation using point-slope form. So I'm going to say y minus this pi root 3 over 3 number is equal to the slope, which is a very bad number, square root of 3 plus pi over 3, multiplied by x minus the x-coordinate, pi over 3. Okay. Now, kind of the point I was trying to make here is that here is a very clear case of you don't want to take this and put it in the slope-intercept form. Clearly, right? The numbers are bad. Just leave it in point-slope form, okay? Be happy. We're done. We've got a good, solid answer. We've written an equation for the line tangent to the graph of y equals 2x sine x at the point where x equals pi over 3. You know, nobody can ever ask you to write the equation for the line because there is not just one equation that works. All right, now let's move on and talk about the quotient rule. We'll come back and do a couple more product rule examples at the end of this video, but for now, let's talk about the quotient rule. Okay? We're going to take the derivative of a quotient. Okay? You could go through and you could do like, you know, x minus 5 over x squared plus 1 or something, and you could see that you cannot, in fact, take the derivative of the quotient by taking the quotient of the derivatives. Okay? It doesn't work like that. What we need is a quotient rule. And what I forgot to mention with the product rule was that the proofs of these rules are definitely at y'all's level. They are algebraic, and they are not terribly interesting, and they don't give you any additional understanding as to why the rule works. So I'm including those proofs as a separate video. So if you're interested in that, you know, you should probably go into my channel and search for, you know, the quotient rule proof or product rule proof or power rule proof, you know, any of these proofs. And, you know, that's where you'll find the proofs of these things, okay? Because it would be remiss of me to give you these rules and not show you why they're true, right? I don't do that. I'm going to always show you why stuff is true. I just might not include it in the primary video. All right, so the derivative of the quotient is the bottom times the derivative of the top. Now notice I am not calling these in terms of g and f, because if you try to commit this to memory in terms of f and g, you're going to end up getting tricked when inevitably we ask you about the derivative of g divided by f, right? All of a sudden it's like, what's the top, what's the bottom? Just remember it in terms of top and bottom. Bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. This is another one that we are in need of committing to memory. We need to just know this. So what was I going to say about this? That's what we say. Oh, okay. Again, you need to probably say it out loud when you're working the homework tonight or tomorrow night, whatever. But I'm going to write it again. This is equal to the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. And we need to commit that to memory and just to understand why that fraction bar, the color is not coming back on top of the highlighting. Very frustrating. It'll be all right though. We're about to navigate away anyway. All right, let's work an example. Let me work one, and then y'all can work a couple, something like that. Y is equal to 2x plus the log of x divided by 4x squared. Find dy dx. Okay, well, we're going to need to use the quotient rule because I've got the quotients of two different functions. So what I'm going to say is that dy dx is the bottom times the derivative of the top. All right, what's the derivative of 2x? 2, yes. Okay. What about the derivative of log of x? That one's one that it's been a little longer since we talked about. I mean, I guess it was last time, but you haven't really used it. Yeah, it's 1 over x. Okay. So 2 plus 1 over x minus the top times the derivative of the bottom. Okay, so I'm going to bring the power down, multiply by 4, so it's 8. And then I'm going to knock the power down by 1, so it would be just 8x to the first. Divided by the bottom squared. 4x squared, not what I was doing there. All right, now, you know, if you write the denominator as 16x to the 4th, good for you. If you distribute those things and cancel off some terms, which I'm pretty sure you'd be able to, because I see an 8x squared and a negative 16x squared that would happen. That's fine. It's equivalent to my answer, and honestly, it's no better. Okay, it's not going to work any differently. You plug a given x value in, you're going to get the same result I do. Just different calculations. So I recommend you just stop right there and be happy. Move on and do another problem. Keep practicing the quotient rule, because that's what y'all need at this point. You need to practice the product rule, you need to practice the quotient rule until they become second nature. Right. Next, let's take a step back and look at some of the derivatives I talked to y'all about last time. The derivative of secant of x, the derivative of tangent of x, cosecant, cotangent. All right. I'm just going to do one of them and kind of show you how it would be done. And you can do the other ones on your own if you're interested. Okay? So I'm going to start with y equals tangent x. Okay, so the derivative of tangent x with respect to x. All right, well, if you don't know it, well, what I'm going to do is I'm going to write this as the derivative of sine x divided by cosine x. And I'm going to use the quotient rule. And now maybe you're starting to remember that it's bottom times the derivative of the top. All right, I need to zoom out. Minus the top times the derivative of the bottom. Yes, definitely negative sign. Thank you. Oh, sorry, I was just getting ahead of myself. Divided by the bottom squared. So that's cosine squared x. All right. Well, this fraction, I'm going to start to, simplify it a little bit, clean it up. Cosine x times cosine x is cosine squared x plus sine squared x. Now, what is that, the numerator? You remember? 1. Yeah, 1. Yeah, you must have had a really good pre-cal teacher. I actually know for a fact that you did have a really good pre-cal teacher. It wasn't me. That's probably why you remembered. All right, and then the cosine squared in the denominator is going to stay there. All right, and so now I'm going to say that's 1 over cosine squared x, which we could call secant squared x, which is what I told you last time that the derivative of tangent was. Okay, should you be interested in taking the derivative of, say, secant x, what you're going to do is you're going to rewrite secant as 1 over cosine. Okay? And then you're going to do the quotient rule on that, just like I did. You're not going to need to apply any trig identities, except maybe that, tangent is sine over cosine, and that secant is 1 over cosine. Okay? So I'll tell you the derivative of secant is secant x times tangent x. That's something, if you wanted to try this at home, you should pause the video and try to demonstrate that yourself. The derivative of cotangent of x is negative cosecant squared of x. You could try that one, just doing cosine over sine. Or you could try the derivative of cosecant, which is going to be negative cosecant x times cotangent x. Basically all with the same techniques. Okay, but in the interest of keeping this video short, I'm just going to do the derivative of tangent for you and tell you that you could, on your own, do the rest of them. Okay, next we've got a data in the table problem. Okay, this is very common in AP Calculus, right? We follow Rule 4. We try to display functions graphically, numerically, algebraically, and verbally. Okay. Data in the table is really nice because it gives you some information about a function, but not all the information about a function. The thing is, they'll always give you just enough. Right? So, if p of x is equal to x to the third multiplied by f of x, then p prime of 2 is equal to what? All right, well, we're going to need to first find p prime of x using the product rule. And that's going to be 3x squared, leave f of x the same, then leave x to the third the same, and take the derivative of f. Well, I don't know what f is, but I'll just write f prime of x. And luckily, I've got, a little bit of information on f prime. So now I'm going to, I want to find p prime of 2. So I'm going to plug into where I see x. So 3 times 4 is 12 times f of 2 plus 2 to the third is 8 times f prime of 2. And then I'm going to get f of 2 and f prime of 2 from the table. All right, so this is 12 times f of 2 is 1. And plus 8 times f prime of 2 is 7. All right. You can say that that's 12 plus 56 is 68. All right, and then I've got this question already. I'm starting in on this. Do not memorize the quotient rule in terms of f and g. That is not a good idea. okay? Because if h of x is g of x divided by f of x, then h prime of 3 is what? Well, we're going to need to, just like before, I'm going to need to take the derivative, just find h prime of x using the quotient rule. So it's bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. Okay, well, that means that h prime of 3 is going to be f of 3 g prime of 3 minus g of 3 f prime of 3 divided by f of 3 squared. All right, well, then I go over kind of to the right column of the table, and I find that f of 3 is negative 3. G prime of 3 is 2, minus g of 3 is 6 times f prime of 3 was 0. Okay, that'll be nice. That'll make the calculation a little easier. Divided by f of 3 squared. Well, that's negative 3 squared. So I can do that. That's negative 6 divided by 9. Okay, or negative 2/3, whichever one you like. Okay, higher order derivatives, I think, are something I had planned on talking to you all about last time. I just kind of ran out of time. Maybe I spent too much time going over the test, or I don't know what it was. But anyway, this is going to be second, third, fourth, fifth, 10th derivatives, the notation we use for them, how that works. Okay. So if we say that, y equals sine x, last time we said that we take the derivative, we say that dy dx, the first derivative, is cosine x. Now, if I wanted to take the derivative of the derivative, well, that would be taking the derivative of dy dx. Okay, and that's the reason why we use the notation, the second derivative of y with respect to x both times. We put the second power between the d and the y, but after the x. Okay, is because of that. And that's going to be negative sine of x. Maybe we want to take the derivative of that. We want to analyze the third derivative. Well, I'll say the third derivative of y with respect to x all three times is going to be negative cosine x. Now, the thing is, in this class, this is a single variable calculus class, so it doesn't really, the subtlety of taking the derivative of y with respect to x all three times, well, what else would we take it with respect to, right? But in a multivariable calculus class, you might take the derivative of a function with respect to x and then with respect to y, or with respect to x and then with respect to z twice, or something like that. And that's kind of a different discussion, but that's why, we say it the way we do. All right, and then I'll do the fourth derivative. Oops. All right, and this is sine x. Okay, so it cycled all the way back around and came back to the original. You all ever seen that type of structure before, something that cycles around every 4? Yes, the powers of I. Okay, y'all remember that? How it was like, the first power of I was I, then it was -1, then it was negative I, then it was 1, and then it went back to I. Okay, this is basically the cyclic group of order 4 is really the structure at play here. And if you're interested in that, throw that into the search bar on YouTube. You'll end up with some abstract algebra. This structure is all over the place. Cyclic groups of different orders are things that show up in your lives and in mathematics sometimes, and they're interesting objects, but they are really far beyond the scope of this course. Okay, so another bit of notation, right? We call y f of x sometimes. and we call the derivative f prime of x. And we call the second derivative f double prime. We could even call the third derivative f triple prime. But past triple prime, it's kind of like you'd have to, maybe sometimes, especially with certain people's handwriting, pull out a magnifying glass and start counting the number of tick marks. So we don't want to do that. What we'll do instead is we'll say f's fourth derivative by just putting a parenthesis around the 4. Okay. We can go higher than that. We can go 5th derivative. We can go 10th derivative. We can go 98th derivative. Okay. Just as kind of like a question for thought, what would you say if I asked you what the 30th derivative of x to the 10th power was? What would that be? I took the derivative 30 times of x to the 10. Let's see what that would be. After a certain point, you take the derivative 10 times, you get down to just 1 power of x, then it would be, after that, it would just be a constant, right? And then, yes. And then what's the derivative of constant? 0. Yeah, and then you take the derivative like 20 more times, or maybe 19 more times. I have to think about that. But you would end up with 0. Okay, so basically, that's the type of question that they could ask you, something like that, conceptual question. Is there any actual use for the 30th derivative? I don't know. You'd have to ask a scientist. That's certainly not me. All right, the last thing I got for you in this video is something that kind of never fits in quite right in an AP Calculus class. It's the type of thing that is very rare, but I have seen it on College Board items, so again, I would be foolish to not show you about it at some point in the course. And, now seems like as good a time as any. We need to practice our derivative rules. The normal line is perpendicular to the tangent line at the point of tangents. So you've got, your curve, you've got your tangent line that lies right up against it, and you've got a normal line that sits perpendicular to that. And physicists will know that, normal components of things, normal forces, these are somewhat important sometimes. All right, so for example, so let's do a quick example. Let's write an equation for the normal line to y equals sine squared x and x equals pi over 4. Now this is like, wait a second, dude, you didn't tell me how to take the derivative of the square of a function. How can I do this using the product rule? Sine of x times sine of x, absolutely. That's what I'm going to do. I'm going to get this definition out of it. All right, so I'm going to go over here and I'm going to say y is equal to sine x multiplied by sine x. All right, so I'm going to take the derivative real quick. Okay, sine x multiplied by cosine x, then add in, I guess, cosine x multiplied by sine x. Okay, so in order to write a tangent line, I would need a point and a slope, so I'm going to really need the same thing to write the normal line. So I'm going to start with a point. And x is going to be pi over 4, and y is going to equal the sine of pi over 4 multiplied by the sine of pi over 4. All right, so that's going to be 2 divided by 4, which is a half. So the point is pi over 4 and 1/2. And the slope, well, dy dx, this looks like something I could probably simplify. This is 2 sine x cosine x, which you could actually do a little bit more with if you were just like a type of pre-calculus student that really remembered all your trig identities, but I don't need that. So the slope is going to be 2 times the sine of x times the cosine of x. Okay. Well, but really it's going to be perpendicular to this. Okay, so I'm going to make a little note. All right, so it's going to be perpendicular to 2 times root 2 over 2 times root 2 over 2. Okay, 2 sine x cosine x. So this is looking like 2, 4 over 4. So it's perpendicular to 1. So you think all the way back to algebra 1. What's perpendicular to slope to 1? That would be -1. So the equation of my normal line It's going to be y minus a half is equal to -1 times x minus pi over 4. That's all I got for you today.